surface integrals and flux integrals. It turns out, good news, you already know how to do a surface integral because I taught you how already. Yeah, and a flux integral is a special case of a surface integral. So let's do a quickie review and then we'll get to the new stuff. So some really review is, what do you know about line integrals? They're evaluated along, well, lines, not really lines, but curves. Double integrals are defined on plane regions, 2D, right? Like areas. Triple integrals are defined on solids. Okay, so you got all these different kinds of integrals, line integrals, double integrals, triple integrals. You've learned all of those here in this class. Yeah. So what's something new? Well, now we're going to do a surface integral. Really? Another new thing? Well, yeah, you're going to integrate over a surface. Well, isn't that what a solid is? No, these are different. When you integrate over a solid, you're looking at volume element like dV, like that. When you're doing a double integral, you do dA. Okay, but when you integrate over a surface, you're looking at ds, which is the surface area element, not dV. It's different. Now, so let's do the review because you did this already. So recall from previous lecture when we did a double integral to find surface area, and you even had exams on it. The definition of surface area, if you have a function f and its partial derivatives are continuous on a closed region R in the xy plane, then the area of the surface area of the function z equals fxy over the region R is given by this. This is a surface integral. And you can see the little s there. And we looked at one of these because the integrand is a 1, but the ds stands for surface area element. And that surface area element, which I derived for you in a little mini proof, is pretty hellacious. We did it by doing a area of a parallelogram. I don't know if you recall. I had to do a cross product to get this. It was nasty. Yeah, the magnitude of the cross product was this horrible looking radical. Yep. And that was the surface area element. So there's the review. So what are we going to do that's a little different starting right now? We're going to do a surface integral just like this one. But instead of just a 1 being the integrand, which you may argue, well, it's more than just a 1. It has that horrible radical. Yeah, but the ds, that's the surface area element. We're going to stick something even in front of that radical. So here we go. So let's find the mass of a surface. So here's the surface equation or function. And then the density function, this is different from the surface. Try not to get these mixed up. And it is very confusing because up here when I did the review, I have the surface defined as fxy. And now down here, I'm changing it. And I apologize for that, but I do want you to notice, please notice, that I'm going to change the notation a little bit where the surface, I'll call it G instead. Well, how come? Well, we have too many F's running around. We'll use the F for the density function for the surface. Okay, I know, confusing. So let S be a surface with this equation, Z equals GXY. Let R be the projection of that surface onto the XY plane. And if you've got G and the partials of G are continuous on your region, and this, which is your density function, is continuous on your surface S, then the surface integral of F over S looks like this, double S, and then you put your density function in here, and then ds, where ds represents the surface area element. Now, I don't know how to integrate that. You have to know how to turn it into a regular double integral. So to turn it into a regular double integral, you do it like this. You integrate over the region R, which is the projection of the surface onto the XY plane. fxyz, you just copy it down. And then the ds, which is still that surface area element, looks like the square root of 1 plus the partial of little g with respect to x squared plus the partial of little g with respect to y squared dA. Yep. Now, there's one little extra here that you have to do. When you're doing a double integral, and you know this already, this is review, you're only allowed to have two variables involved, x and y, typically. But it looks like we have three variables involved, x, y, and z. What the heck? That's not okay. So what you're going to need to do if z does show up in your density function is you need to replace z with the surface equations, g of x, y, and then you'll get everything back to x's and y's. Then you can actually integrate. So that's not in the theorem. They don't tell you that explicitly, but I'm telling you right now, when we do some actual examples, you're going to need to remember that. So please remember, that's key. Okay, now let's go over some common student errors, which you may go, oh yeah, I promise I won't do that. But you might, you may forget what I'm going to write down here. When I grade these, especially on the final, these are worth a lot of points, and I see students making these common errors. So one of the things they forget to do is they forget to replace the z with the gxy, which I just talked about. And what's another common student error? They accidentally, of course they do it accidentally, they didn't mean to, use the density function fxyz's partials instead of the z equals gxy partials. So what am I saying? So these partials that you see underneath the radical, the gx and the gy, sometimes students, when they're doing a problem, they, all these functions running around and it gets confusing and they're like, and they accidentally put fx and fy here, and that's not okay. So please use the surface partials, not the density function partials. So those are common student errors I've seen. And if you make either one of these errors, you're not going to get much credit. I can't really give it to you, not even partial credit. So you have to be really careful when you're doing a surface integral. Okay, so I'm going to do a couple, and then I have one lined up for you that's not in the course reader. Yeah, you're going to give it a shot. Why not? So these two I'll do. They are a little bit different flavor. What I do want you to know is that both of them are surface integrals, because you see an S here with the ds. That is standing for the surface area element there. And both of them look like they have a z here for the density function, which is not good, because you're going to have to replace z with something. Replace it with what? Well, for this problem, example 1, they didn't even give you the surface equation solved for z. So you're going to have to do that as step 1. So step 1, solve this plane equation, 2x plus y plus 2z equals 6 for z. And that's pretty easy. You've done something like that before. And when I do that, I'll get z equals a half, 6 minus 2x minus y. Okay, so when we replace this z, we will replace this z with the 1/2 6 minus 2x minus y before we integrate. Okay, so then what? All right, the next thing is that we need to get, since this is really the g right here. So let me just label him. He's the g. So let's get step 2, get little gx and little gy. That's easy. So you'll go, all right, take the partial with respect to x of the surface, which is just a plane. A half times the partial with respect to x is -2, but then that ends up being -1. Oh, that was easy. And then the partial with respect to y, you got the half in there. And then the partial of 6 minus 2x minus y with respect to y is -1. I get -1/2. Okay, fine. So then this horrible looking radical, which is 1 plus the gx squared plus the gy squared, ends up looking like square root of 1 plus -1 squared plus -1/2 squared. Oh, it's going to be a constant. Does that always happen? No. But when it does, it's nice. So clean this up a little bit. This is 1 plus 1, which is 2. 2 plus 1/4. Ooh, I get square root of 9/4, but that's the same as square root of 9 over square root of 4, which is 3/2. Okay, save that for later. Now, and this is step 3, this surface integral, which basically represents the mass of the surface in question here, the plane, where the integrand is some density function. Okay, it's going to turn into a regular double integral over R, and you'll have the y squared plus 2y, but in place of the z there, remember, we're going to put the surface, the 1/2 6 minus 2x minus y. And then we have the ds. This ds here gets replaced with, oh, not too bad, 3/2 dA. Okay, so now go integrate this beast. Well, I got to do some cleanup here and also figure out how to iterate the double integral. How do I put limits on? So let's look at step 4 now. Let's get the region R. What does that look like in the xy plane? Well, if you project this plane equation down onto the xy plane, so in the xy plane, we know that z is equal to 0. So if you force z equal to 0 in that equation, you'll get this. And if you solve it for y, you get y equals 6 minus 2x. So that looks something like so. And they did tell us the first octant. That's important because that means we're going to be stuck in the first quadrant. So here is the region R. And this line is y equals 6 minus 2x's graph. Okay, now what? Well, when you iterate, that means put limits on your little double integral, and I'm going to choose my order of integration to be dy dx. That's my favorite. This 3/2, I'll stick it out in front. And then this 2y1/2, if I distribute it over that difference, I'll have like, oh dear, y squared plus what? 6y minus 2xy minus y squared. Okay, and hey, these y squareds cancel. Cool beans, man. So what does that mean? That means I only have to worry about integrating 6y minus 2xy and dy dx. So here the outer limits are pure numbers. So on this triangular region here, x looks like it's going from 0 to 3, and y is going from 0 to 6 minus 2x. Okay, so I'll just do one step and then I'll call it, and then I'll say use your graphing calculator. So if I integrate 6y minus 2xy with respect to y, I'll get, let's see, the first term, 3y squared minus xy squared. And I'll evaluate that between 0 and 6 minus 2x. And so then when I replace y with 6 minus 2x, because replacing with the 0, it's going to all go to 0. So I'm going to have that. Oof. Yeah, you know, you'd have to FOIL all this mess out. I'll just say graphing calculator, come to the rescue. You know, use your F and INT, and I get 243 halves. Okay, there's the surface integral. Not too hard. And let's just recap. The relevant application is basically mass of your surface. So we've got a surface. That's your little g. You have a density function. And then if your density function even has a z in it, replace the z with the surface equation. And I almost always choose problems on my quizzes and exams where there is a z on there. Some of the homework's real easy where the density function doesn't include a z. I put one in there almost every time on quizzes and exams, just to let you know. Okay, so any questions on example 1? You guys are awfully quiet. Okay. So let's do example 2. So why are we doing another one? It's like, this one has a little bit different flavor to it. So you'll see in a moment why. We got a cone. And if you graphed this cone, it's actually a double napped cone. But it turns out we don't need both naps. We only need the upper one. Well, how come? Because they're saying z equals 1 and z equals 4. So if you graphed this surface that we're integrating over, you're going to look at a portion of the cone between z equals 1 and z equals 4. So it kind of looks like that. So it intersects the z-axis at 1 and also at 4. And if you plug z equals 1 into this cone equation, you'll get 1 squared equals x squared plus y squared. And if you plug the 4 in there, you get 4 squared equals x squared plus y squared. And it turns out the projection of this surface onto the xy plane, the shadow, if you will, it's making is looking like a donut. Yeah. And that's important for us to get, because when we iterate the double integral, we're going to care about what's going on in the xy plane. This surface doesn't cut through the xy plane. So you don't want to like set z equal to 0 like you did in the other problem. That's not going to work. This plane right here, if you did graph it, which I didn't, but you guys know how to graph planes in 3D. We went over that like second week of class. You know, the x-intercept is a 3 after setting y and z equal to 0. The y-intercept looks like it's a 6. The z-intercept looks like a 3. So here's the portion of the plane, that's your surface, that we were integrating over. And you can see that it cuts through the xy plane as it, because this diagonal line is the trace. Unlike this surface here that's hovering above the xy plane, it never cuts in there. So you have to consider the idea of the projection, the shadow. So the shadow that this guy makes on the xy plane is this donut, 2 concentric circles. So it's outside of the circle of radius 1, but inside a circle of radius 4. Do you guys note that we're probably going to have to convert to polar based on this region R?
Yeah.
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 We definitely are. And so that's the big difference between this example and the other one. I wanted you to see both, you know, rectangular coordinates, which we just did, and then one that's going to end up needing to convert to polar. Okay, but before we do that, step 1, solve z squared equals x squared plus y squared for z. Well, that's easy because we'll get plus or minus the square root of x squared plus y squared. But we're only going to choose the plus because we're taking the z cone portion that's above the xy plane. That's positive. So I'm going to rewrite this using exponents because this z is our little g in the theorem. That's the surface. So step 2 is get the partials. Yep. So this is not going to be fun because we're going to need the chain rule. So when you use the chain rule and take the derivative of x squared plus y squared to the 1/2 power, so when you take the derivative with respect to x, careful, I get that. And when I rewrite it and simplify, and I like to rewrite with positive exponents, but then I get to the 1/2 power, which is square root, back in there. And gy, similar chain rule going on here. And when I clean it up, you know, reduce it essentially and rewrite it. Okay. So then I get that. Okay, now what? Well, step 3, kind of like we did up here, well, before we get to step 3, let's consider this radical, which is the part of that surface area element that looks pretty gross. So this is not going to be nice. It's not going to be a constant like that last guy was. Yeah, it doesn't look like it. Wow. So watch closely because it actually is going to end up being a constant. Okay, so if you look at this mess, which is like, oh man, this is horrible. Oh man, I hope I don't have to integrate this. Awful. Well, if you try to rewrite as a single quotient, and this is just algebra now, so you try to find an LCD. Well, this one, you know, his denominator is 1, but if we beef him up a little bit and multiply both his numerator and denominator by the common denominator, then, oh, we can add all 3 of these terms together because they all share the common denominator of square root of x squared plus y squared. Oh boy, this is going really slow. So then I add up everybody's numerators. Yeah. Oh, I got some like terms in the numerator. Yeah, there's 2x squared plus 2y squared. Oh, let's go further. If I factor out a 2 from the numerator, then it looks like I can reduce this to lowest terms, and I will. So I go, and I just get square root of 2. Ah, wow. Ah, that's perfect. And there's my meme. I used to be good at math, and I took vector calculus. I know, right? You know, some people, by the time they get to this part in Calc 3, they start thinking, yeah, you know, maybe Calc 2 was easier. Maybe I like sequences and series now. I don't know. Those sequences and series are starting to look really great. I miss those. Okay. So now what? Well, now step 3, you can kind of put it all together. We've got the double integral, that's a surface integral, and you want to rewrite it as a regular double integral over the region, which is that donut. And so you've got x squared and then z, and then the surface area element is square root of 2 dA. So what was z again? What do you put in those parentheses? So you're going to put that. Oh no, that looks terrible. Yeah, I know, but don't worry about it because we're going to convert to polar here in 2 shakes and it'll be not too bad like that. Okay, so there's your little g essentially. You know, you replace it with little g. Okay, well this is still pretty gross. And so if you look at your region and you convert to polar, it looks like r is going between 1 and 4. Yep. And theta is going from 0 to 2 pi because you're doing a full revolution. So when we convert to polar, so this is sort of your way to get out of integrating that, which would probably require trig sub or something terrible. I don't know. Oops, not 0, sorry. 1 to 4, x squared, where x is r cos, so we'll square it. Square root of x squared plus y squared, that's square root of r squared, which just simplifies to r. And we've got that square root of 2. And what is the area element in polar? Come on, guys, what do you think?
R dr d theta.
R, be a pirate. So you got a lot of r's going on here because this right here is going to contribute a couple of r's. And I'm going to pull the square root of 2 out. So I combine all of the powers of r into one big old R. And then I can integrate. R to the 4th is pretty easy. That's just going to be r to the 5th over 5 and evaluate that between 1 and 4. So let's do a little bit of scratch over here. What the heck is 4 to the 5th power over 5 minus 1 to the 5th over 5? And it turns out it's 1,024 fifths minus 1/5, which is 1,023 fifths. Okay, well, it's a constant, so I'm just going to pull it out in front of my integral and then worry about integrating cos squared. And you guys should know the drill, power reduction formula, right? Definitely know your power reduction formula because I love this power reduction formula. It's kind of where your Calc 2 comes and saves the day. And this half I like to pull out. So at the same time I do that, I'll integrate the numerator. So I'll have theta plus a half sine 2 theta, and I'll evaluate that between 0 and 2 pi. And the sine term doesn't contribute anything because at 2 pi and at 0, he's a big fat 0. So only the theta is going to make a contribution, a non-zero contribution, and that'll be 2 pi. And then after reducing, I'll get 1023 square root of 2 pi, because these twos cancel, fifths, and that's approximately 909.0. And we're done. There's your answer. Whew. That was a little bit more work because of that cone equation, and all the partials of that were kind of ugly. But it ended up not too bad. Yeah, we could integrate it, no problem. So that's a surface integral. So I have a surface integral all in store for you guys. So let's get to it. I'll put you into study buddy groups here. So how about you and a buddy do this surface integral, okay? So you're going to do double double fxyz ds, where your fxyz, that's your density function, is x squared plus y squared plus z squared. Okay. And I'll give you a hint. You are going to need to convert this mess to polar. Yeah. And then the surface S is given by z equals x plus y, and also bounded. It is in the first octant, and also bounded by the cylindrical surface x squared plus y squared, and less than or equal to 1. And you'll stay in that first octant. Okay, so that is all the information you need to do this surface integral. Okay, and I'm giving you a hint, convert to polar. All right, so let's see here how we do. Let me go to breakout rooms. Woo! All right, great rooms. If you can, turn on your mic so you can talk with a buddy and see what happens. Okay. Oh my. All right, so let's try this. Okay. Good luck, guys. Okay, did you guys make some progress here with this surface integral?
Yeah.
A little bit.
A little bit. So hopefully you got that the region of integration is just a quarter of a circle there in the first quadrant. That's your R. So when they're asking you to do this surface integral, you got to get all the ingredients. So step one, you already have your z equals x plus y. There's your surface. So you need to get little gx, and because this is your g, and little gy. Okay, and remember the common student error would be that you accidentally took the partials of f. You don't want to do that. This is your that's your density function, and you don't want to take partials of the density function. You're doing your partials of your surface. So then your square root of 1 plus the gx squared plus the gy squared is going to be a constant. Cool. That's lovely. So then you're like, all right, so then this double integral, which is the surface integral, which looks like this, because that's your fxy ds, is going to be the double integral and then x squared plus y squared plus, and you need to replace the z with something that has x's and y's in it. So what would that be replaced by? Does anybody know? What'd you get there?
X plus Y squared.
Yes, you're going to go x plus y, and then that z is getting squared. And then you've got your surface area element. Don't forget, this ds ended up being square root of 3 dA. Perfect. Now, because the region is a quarter of a circle, it's good to convert to polar. Make this easy for yourself, where r is going to lie between 0 and 1, and theta will go from 0 to pi halves. And I'm going to pull the square root of 3 out because it's just a multiple, and then x squared plus y squared, well, that's r squared, plus, now this thing here, careful, that's not r squared. You want to FOIL that out. Like that. So you need to FOIL that. If you didn't, oops. Now, if I rewrite it where the x squared plus y squared is right next to each other, I can replace the x squared plus y squared with r squared. Now, the 2xy is not so pretty. You're going to have to replace x with the conversion formula r cos theta and y with r sine theta. And then, of course, be a pirate. Your area element for polar is r drd theta. Yep. And you can combine these powers of r, so I get 2r squared. And then you want to distribute this r so that you have everything in place. So you're going to have what? 2r cubed plus 2r cubed cos theta sine theta, like this. Now what I did, and you didn't have to do this, but I just don't like it to be too messy. So I factored out the 2r cubed before I integrate with respect to r. This is just personal choice, just because the 1 plus cosine is just a constant multiple. And so I'll just kind of put it over to the side. And then the integral of 2r cubed is r to the 4th over 2, and I'll evaluate that between 0 and 1. That just ends up being a half. So then I can just pull the half out. And then when I integrate 1 plus cos theta sine theta with respect to theta, I can use u sub with the power rule. Here u is sine theta and du is cos. So this is just looking like the integral of u du, which is u squared over 2. So then my antiderivative with respect to theta looks like this. And you're going to go from 0 to pi halves. So the pi halves is going to be the one that contributes to everything, because the 0 is going to make theta and the sine term go to 0. So we don't care about that. But you're going to have pi halves plus sine squared pi halves over 2. And I hope you remember that sine of pi halves is a nice number. What is it? Anybody know? Sine of pi halves? It's not 0.
1.
Yeah. So you got that. So you're like, oh, so square root of 3 halves, pi halves, plus a half. And that is your final answer. You can leave it like that. Or if you like, you can maybe rewrite it a little bit by pulling out the half. I don't know if that makes it look any better. It's still a weird number. Anybody get that?
Yes.
Okay. So what's the moral of the story here? When you're doing a surface integral, you got to kind of keep all your functions straight. So you have to make sure that you don't take the partials of something that's, not the surface. Okay. And this represents the mass of the surface. Fine. All right. Any questions on that before we do a wrap up and do flux integrals? Okay, I'll just assume you're all good. All
Yeah.
right.
Yeah, good.
You're good. All right, so let's do a quick summary of scalar surface integrals, because the next kind of surface integral we're going to do is a vector field surface integral. You knew this was coming, right? Vector fields aren't going away. So you've already seen that if a function f is defined on the surface, but fxyz is 1, so you have like a 1 here, then that's just area of the surface. Fine. But if you stick something in there that's a density function, this represents the mass of that lamina, of that surface. Fine. So those are your two applications of these scalar surface integrals. So now we're going to jack it up a little bit. We're going to look at a surface integral that isn't considered a scalar one. So folks, I want you to get the analog between this stuff and line integrals. When we did line integrals, type 1 was a scalar line integral where it basically represented a mass of a wire. And the scalar surface integrals represent mass of a surface. And then the other two line integrals involved vector fields. So those kinds of line integrals represented work done on an object, or it represented flux. So we're going to get into this other kind of surface integral, but before we do, let's do some preparation work. And the preparation work is kind of cool. You may have some fun. Let's talk about orienting a surface. What the heck? When you get a surface, you want to figure out, what's pointing out from the surface and what's pointing in, because the surface may not be closed. So we use unit normal vectors on the surface, and you saw not unit normal vectors, but we used unit normal vectors, excuse me, just normal vector. Remember when we were trying to find the tangent plane to a surface? So you guys know how to find a normal vector to a surface. So we're going to use unit normal vectors to help induce an orientation to a surface S in space. Now let's do a quick definition of what an orientable surface is. A surface is called orientable if the, there's a little typo there. It should be unit normal vector n can be defined at every non-boundary point of S in such a way that the normal vectors vary continuously over S. What the heck does that mean? If this is possible, S is called an oriented surface. So here's the key that I want you to get. An orientable surface has two distinct sides. Okay, if you've got a nice surface like a sphere, that has two distinct sides to it. It's got the outer side and the pointing in. So if you looked at a sphere, let's say here's a sphere, you can look at a whole bunch of little teeny tiny unit normal vectors sticking out of it. These are all ends, and it is orientable. On the other hand, take the same sphere, but let's say you wanted to orient it inward. So you could take all the unit normal vectors to the sphere that point inward, because the sphere does have two distinct sides to that surface. Okay, so the question is, do all surfaces have two distinct sides? No. No, I don't want to zoom there. No, I don't want to do cancel. No. There we go. So the answer is no, not all surfaces have two distinct sides. So what do you mean? Now, if we were face to face, which we're not, I would tear up a piece of paper and twist it around and do a little twisty in it and tape it together. But we're not. So instead, I'll show you a picture of a Mebius strip. And this is a nice meme. That's a Mebius strip, because if you go around here and then, so you start here and then you go all the way around, you end up on the underside of the surface. You can't get back to where you started, this Mebius strip. So what's funny about this meme is the teacher said we're allowed to bring a single side paper for notes. This is actually a single side because of the Mebius strip. It's not orientable because it doesn't have two distinct sides. Funny, huh? So we're going to use the gradient vector to find a unit normal vector to a surface. You've done this before when you were finding equations of tangent planes where the tangent plane was tangent to a surface. So it's been done. So let's just start off again. Here's your, say, capping surface, z equals g x y. This is from like a month or two ago. And if instead of doing where we were finding tangent planes, we're going to do something else with it. Now remember, when we did this from a month or two ago, I did ask you to subtract z from both sides and get what's called the general representation of the surface. The general representation of the surface, everything on one side and 0 on the other. And we'll call this big G. Now, back 3 months ago or 2 months ago when we did this, we, instead of little g, we had little f, and we renamed it big F instead. So I'm sorry about the changing of letters now, but you know, whether it's big G or big F, either way. So this is the general representation of the surface instead of z equals little g. So once you've got this, you go get the gradient of big G, and that will give you something that's orthogonal to your surface. So if you get like, here's del G sticking out of the surface like that. And we're just going to unitize it. That's all. So N is going to be the unitized gradient. You guys know how to unitize vectors. And so here's the thing that you need to not lose sight on. Since we got z over on this side, z would be, if we did the partials, if we did big Gx, big Gy, big Gz, Gz would be -1, but that's oriented down because the -1 is pointing down. So, and that's okay, but what if you want to orient, what if you want to orient up? So what you're going to do instead is, instead of subtracting z from both sides, how about take this equation and subtract the subtract the little g from both sides instead to get everything on one side and 0 on the other. So you've got this, and this should say equals 0. So why is that going to be so different? Well, we're still going to get a normal vector to the surface. And we care about whether it's oriented up or down now. When we were doing tangent planes, didn't care whether it was oriented up or down. It was still a normal vector to the plane, and we were just trying to get a plane equation. Now we care if it's oriented up or down, because with flux, you're going to care. So if you read my announcement, we're going to determine flux, like the amount of water flowing through your surface, or as I mentioned, you know, kind of just funny tongue-in-cheek, the amount of bananas flowing across your surface. So you're going to have a negative little gx, negative little gy, +1. That's your gz essentially. And you're going to unitize it. So you're going to take the square root of 1 plus gx squared plus gy squared. So this is the unit normal vector oriented upward, as opposed to downward. Sometimes you do need the downward version. So the downward version is just going to be pointing in the opposite direction as the upward. So we're just going to basically take this vector and take everything opposite in sign here. So you'll have positive gx, positive gy, -1, and you still have the same magnitude of the vector. Okay, so are we getting somewhere? Yeah, we're getting somewhere. So this one is oriented down. downward. We're getting somewhere, don't worry. I think I put something in here about another non-orientable surface. It should be that that Klein surface. There it is, the Klein bottle. Also another very weird surface that is not orientable. You can read about it on your own. But the Möbius strip is related. So just kind of some fun facts to impress your friends. We're not going to be dealing with Möbius strips or Klein bottles because they are not orientable surfaces. We're going to only care about surfaces that are orientable. Okay, now we're getting ready. One of the principal applications of the vector form of surface integrals relates to the flow of a fluid through a surface S. And these kinds of integrals are known as flux integrals. So imagine your surface S is submerged in some fluid, like a jacuzzi or a bathtub, having some velocity field. And let delta S, that's delta S here, like a little small patch of surface area over which that vector field is nearly constant. So you can kind of get your mind around it here. The amount of fluid flowing across that little patch per unit time is approximated by the volume of this column. So you have a little stopwatch and you go click and then stop. And then you'd have that much fluid just flew past your little patch. Okay, or bananas, whatever you're trying to monitor, water, bananas, you know, whatever the material that you're trying to figure out the flux of. So the volume of the column is the height of this column multiplied by the area of the base. Well, the base is just that little patch. So that's just like that little delta S, the surface area of the base. But what about the height? Well, this isn't really a straight up and down rectangular box. So you're going to need to project this sort of slanted force field onto, you know, if I were to draw this box a little bit better, it's kind of slanted here. So the height here is going to be, if this n is your normal vector, you're going to want to project your force field onto that unit normal vector. And that's why you're going to get F dotted with n. That's a dot product, but it's basically you're projecting F onto n. It's like the component of F that's basically contributing to the flux. So the total volume of fluid that flows across your surface is called the flux of F across the surface S. And this is what you're going to be asked to get on these kinds of problems. They're going to go, hey, find the flux of the vector field across this surface. Okay, that's every single one of these problems. So let's look at a flux integral. Okay. So you got a vector field, MNP, and you've got continuous first partials, and you've got some surface that's orientable, and you can orient it by a unit normal vector n. Then the flux integral of F across S it's going to have this look to it. Double integral, it'll have an S down there, but then the integrand is not going to be a density function like it was, 15 minutes ago, which you just did for me. It's going to be this dot product. Your vector field dotted with your unit normal vector. Now, good news, you're never going to really have to do this. You are going to have to do a dot product, but it's not going to be as nasty as, I'm going to do the cleanup on this. So watch the cleanup. Here is the cleanup. The N, which you already saw me get up here, it was that unitized unit normal vector here to the surface. It was either, we'll use the one here that's oriented up. It's this big mess here. Okay. That guy. Yucky. So what we're going to do is we're going to look at the NDS portion of this flux integral and do a little bit of cleanup so you never have to do this yuckiness again. NDS. There's the N. It's the gradient unitized. And then remember, DS is that area element, the surface area element, which we already talked about. It's that horrible radical dA. But this radical down here, when we were unitizing the unit normal vector, is exactly the same as the surface area element. Oh my God. So that radical cancels. Lovely. And you never have to worry about it again when you're doing a flux integral. You do when you're doing one of those surface integrals. So all that's left is your gradient and then the dA. So here's the theorem on how to evaluate one of these flux integrals. After the radicals cancel, you still have to worry about doing a dot product, but not with any radicals involved. So you turn it into a regular double integral over the region. And again, the region is the surface projected onto your XY plane. And you're going to take the dot product of the vector field with your gradient, dA. And this is if you're oriented upward, which you usually are. It's more common to orient up. But if they wanted you to orient down, just because you may have some really weird problem, and I'll do one sometime this week. If you are figuring out a flux oriented in the opposite direction, you'd have positive gx, positive gy, -1 dA. And this is for if your surface is oriented downward, okay? And sometimes it is, but it's more rare. And that's it. That's evaluating a flux integral. Really? Yeah, we're going to do an example. Don't worry, I got one planned. I'm not going to leave you hanging. Yeah, we got to do an example of one. It's not that bad. You just plug and chug and hope it's integrable. Of course. Of course. So here's a classic flux integral type problem. So you've got a surface and have your surface be the part of the paraboloid. And if I had to graph that paraboloid, it's just a downward facing paraboloid. Looks like this. So that's a surface. And this is some vector field. Well, I don't know. What does that vector field look like? I mean, if you had to graph it, you know, it'd be some fluid flow or something. Okay. And so, in fact, I'd like to graph it. What the heck? I'm always interested in this stuff. Let's graph this vector field just to see just kind of all the vectors and the weirdness of it. So we're going to have a 3 vector equal to another 3 vector. And so what do we have here? 3x, 3y, z. 3x, 3y, and then z. So z just stays itself. Okay, let's hit it. What does this puppy look like? Ooh, whoa. Nice. Oops, it disappeared. Where is it? Okay, so if you can see this a little bit, there it is. Whoa, it's making me dizzy. So you can kind of see that it's a lot of flowing, whooshing vectors there. If we change color, change it to yellow. Oh, yeah. Okay, so there's your jacuzzi flow right there. Nice. So it's flowing. You can imagine all these all this fluid flowing through your paraboloid that you're going to submerge into your bathtub. Okay, and you're just trying to figure out how much water is going to flow across the boundary of your surface, or bananas, or whatever it is you're monitoring that's flowing through your. Oh, it would be kind of hard for a banana to make it through a surface unless it was a very porous surface, I imagine. Okay. So there you have it. Here's your vector field. Okay, so we're going to find the flux of this vector field through our paraboloid surface. Fine. So this is our z. So I'm going to get little gx, which is -2x, and little gy, the partial with respect to y. And then when we get our flux, this is what a generic flux integral looks like. It's going to be a double integral over some region. We'll figure that out in a moment. And you're going to take this dot product with, and we want oriented up. So we're going to have -gx, -gy, +1. Okay? So be careful because you have these negatives here. And I don't like to see z in a double integral because I only want to see x's and y's. So what do you think we're going to replace this with? Any ideas?
Nine minus x squared minus y squared.
You got it. The surface itself. And we're going to dot product that with -gx. That's going to be -2x. -gy minus 2y, 1. Okay. So let's do the dot product first. So you got 3x times 2x. That's going to be 6x squared plus 3y times 2y. So that's 6y squared plus 9 minus x squared minus y squared times 1. Oh, that's not too bad. Like that. But what's the region R? Well, this paraboloid does cut through the xy plane. And so if you set z equal to 0, you would see that the trace that it's making in the xy plane is, oh, a circle centered at the origin of radius 3. Okay, so that's kind of nice, right? Because that means we can convert to polar since r is going between 0 and 3 and theta is going from 0 to 2 pi. Fine. So we're going to convert to polar. So this is 6x squared plus y squared, which when we rewrite it is 6r squared. And then this is 9 minus x squared plus y squared, so 9 minus r squared. And I can combine my r squared terms in a moment. The dA, r, dr, d theta. And you know the drill. I mean, you're going to basically combine your r squareds. You're going to have 5r squared plus 9. And then when you distribute your r, you're going to have 5r cubed plus 9r. And you're going to want to integrate that. And I'm just going to put et cetera, because I'm running a little short on time. And this doesn't have any surprises when we're integrating. The final answer, and I'll let you figure this rest of this out, is 567 pi halves. And that's your flux. Now, what does it mean when it's a positive number? It means that you get really mad at your Surface Pro for being annoying with Windows security. Collapse that. Please go. No, please go away. Okay. It means that the fluid that's flowing across your boundary, which is your paraboloid here, since you were orienting it with a bunch of unit normal vectors pointing upward, your fluid will be pointing in the same direction as those unit normal vectors. So more fluid is flowing out in that direction than flowing back in the opposite direction. Now, if you got a negative number, which is totally possible, it just means there's more fluid flowing inward than there is outward. And you could easily get 0 also when you're doing a flux integral. That just means the amount of fluid flowing out is canceled out by the amount of fluid flowing back in. Yeah, same. Okay. Let's do some true false, because you know me, I always like to throw a true false question or two on an exam. And this exam will be no different. Check out letter A, true or false. If the surface S is given by all ordered triples x, y, z, such that x lies between 0 and 1, y lies between 0 and 1, and z is equal to x, then this scalar surface integral, and here's the density function, fx, y, z, can be rewritten as a regular double integral that looks like that. And they did replace the z like they were supposed to, which is good because z got replaced with x. So that's good. So far, so good. Does this look like it's true or not?
True. Oh, wait.
I say false.
You forgot the radical, didn't it?
Yeah, you forgot your radical. So this is a big old false because this is missing. Well, what is it? Well, let's see. The partial with respect to x is 1. The partial with respect to y, because z equals x doesn't have any y's. So it's missing a square root of 2. Now, if there were a square root of 2 in there, then I would say it would have been true. But they forgot to get the surface area element. And folks, the surface area element is super important when you're doing a surface integral. So please don't forget it. Okay, moving on to letter B. Let fxy be continuous on a smooth curve. This doesn't look like they're doing a surface integral. So here's a vector valued function and time going from a to b seconds. So this, folks, is a scalar line integral. This is type 1. This is a scalar line integral. Would you convert it to a regular integral by replacing, the x's and y's with x of t, y of t, and then your arc length element gets replaced with that? True or false?
True.
Well, let's look at the arc length element. The arc length element, remember, is it involves the magnitude of speed.
Yes.
So this 1 is no bueno. False. Well, the surface area element had a 1. That's different. That's the surface area element. That's true. But the arc length element does not involve a term of 1 underneath the radical. So please don't get these confused. That's why I put these at the very end of the lecture, to make sure you kind of keep it straight in your mind. And yes, it matters. Arc length element, little ds, is very different from surface area element, d big S. Big S and little s are two different entities. Big S, surface. Little s, arc length. Big S is surface area. Okay, one more. The flux of a vector field across a curve can be computed using a line integral. So if you had a curve, and I claim it was a closed curve like this, you can definitely get a flux using a line integral. So it's the alternate version of Green's. So if you remember, there's two versions of Green's theorem. The flux version, which I gave you, is this line integral, mdy minus ndx, which you can rewrite as a double integral, where you take the divergence of the vector field. So this right here, so this line integral is like that, and so the answer is true. I can't write. It's not happy. And so the answer is yucky. True. Totally can find the flux of a vector field across a curve. Well, what about flux across a surface? Yes, we just did flux across a surface. That's that guy right there. And you can also do flux across a curve. You can do both. So I hope you're making some connections in your mind with all this vector calculus stuff. I know it can be confusing, flux and, you know, whatever else you're doing, circulation. Hopefully after doing some studying, you'll end up getting it. So I was reading this one article, a famous rabbi said, you don't really know a subject until you've reviewed it. Sometimes you need to review it like 101 times before you really know it. So I'll leave you with that kind of thinking, that once you see something that's nice, and you just saw surface integrals and flux integrals today, which is great, but you won't really know it until you've worked with it and reviewed it and, you know, gotten your hands dirty with it a little bit. Okay. So do that. And then if you have any questions, you know where to find me. And Wednesday we have office time. So you're always welcome to ask questions there. Okay. So that is that concludes 17.6.